Section 5.3, Multiplying Decimal Numbers. In this video, we will see 3 steps for multiplying decimal numbers and how to multiply signed decimal numbers, powers of 10, how to multiply decimal numbers by powers of 10, the definition of a circle, the diameter of a circle, and the circumference of a circle, the relation of circumference to diameter, the digits of pi, and how to find the area of a circle. So multiplying decimal numbers involves 2 steps. 1. Multiplying the numbers as whole numbers, ignoring the decimal point, and 2. Placing the decimal point in the correct position in the product or answer. For example, consider, which asks us to find the product of 7/10 and 8/100. We could change these decimal numbers to fractions, then multiply, changing 7/10 to 7 over 10 and 8/100 to 8 over 100. Then the numerators multiplied together is 56 and the denominators multiplied together is 1000. The product is 56 over 1000 or 56 thousandths, which as a decimal is written 56 thousandths. Important observation. There are 2 very important observations to be made about the example. 1. In fractional form, 7 over 10ths times 8 over 100 equals 56 over 1000. Note that the numerator of the product is found by taking the product of the whole number 7 and 8. That is, you ignore the decimal points in 7/10 and 8/100 and multiply 7 and 8 as if they were whole numbers. 2. The first factor, 7/10, has 1 digit to the right of the decimal point. Its fractional equivalent, 7 over 10, has 1 0 in its denominator. The second factor, 8/100, has 2 digits to the right of the decimal point. Its fractional equivalent, 8 over 100, has 2 zeros in its denominator. Therefore, the product, 56 thousandths, is forced to have 3 zeros in its denominator, and its decimal equivalent must therefore have 3 digits to the right of the decimal point. Let's look at another example. Example 1. Simplify 2 and 34/100 times 1 and 2/10. Solution. Change the decimal numbers 2 and 34/100 and 1 and 2/10 to fractions, then multiply. So 2 and 34/100 becomes 2 and 34 over 100. 1 and 2/10 becomes 1 and 2 over 10. Change these to improper fractions. 2 and 34/100 is equivalent to the improper fraction 234 over 100. And 1 and 2/10 is equivalent to the improper fraction 12 over 10. Multiply the numerators and denominators. 234 times 12 in the numerators is 2,808. And 100 times 10 in the denominators is 1,000 in the denominator. Change this to a mixed fraction. 2,808 over 1,000 is equivalent to 2 and 808 over 1,000. And then change this back to a decimal to get 2 and 808 thousandths. Important observation. We make the same 2 observations as in the previous example. If we treat the decimal numbers as whole numbers without decimal points, then 234 times 12 equals 2,808, which is the numerator of the fraction 2,808 over 1,000 in the solution shown in example 1. There are also the same digits shown in the answer 2 and 808 thousandths. 2. There are 2 digits to the right of the decimal point in the first factor, 2 and 34/100, and 1 digit to the right of the decimal point in the second factor, 1 and 2/10. This is a total of 3 digits to the right of the decimal points in the factors, which is precisely the same number of digits that appear to the right of the decimal point in the answer 2 and 808 thousandths. The observations made at the end of the previous 2 examples lead us to the following method. Multiplying decimal numbers. To multiply 2 decimal numbers, perform the following steps. 1. Ignore the decimal points in the factors and multiply the 2 factors as if they were whole numbers. 2. Count the number of digits to the right of the decimal point in each factor, sum these 2 numbers. 3. Place the decimal point in the product so that the number of digits to the right of the decimal point equals the sum found in step 2. Example 2. Use the steps outlined in multiplying decimal numbers to find the product in example 1. Solution. We follow the steps outlined in multiplying decimal numbers. 1. The first step is to multiply the factors 2 and 34/100 and 1 and 2/10 as whole numbers, ignoring the decimal points. So we treat them as 12 and 234, multiply 12 times 234 to get 2,808. 2. The second step is to find the sum of the number of digits to the right of the decimal points in each factor. Note that 2 and 34/100 has 2 digits to the right of the decimal point, while 1 and 2/10 has 1 digit to the right of the decimal point. Thus, we have a total of 3 digits to the right of the decimal points in the factors. The third and final step is to place the decimal point in the product or answer so that there are a total of 3 digits to the right of the decimal point. Thus, 2 and 34/100 times 1 and 2/10 equals 2 and 808 thousandths. Note that this is precisely the same solution found in example 1. What follows is a convenient way to arrange your work in vertical format. Example 3. Simplify the product. Solution. We use the convenient vertical format introduced at the end of example 2. Treat the decimals as whole numbers, so it would be 23 times 8,235 to get 189,405. Then the factor 8 and 235 thousandths has 3 digits to the right decimal point, and the factor 2 and 3/10 has 1 digit to the right of the decimal point. Therefore, there must be a total of 4 digits to the right of the decimal point in the product or answer. So the solution is 18 and 9,405 10,000ths. Multiplying signed decimal numbers. The rules governing multiplication of signed decimal numbers are identical to the rules governing multiplication of integers. Like signs. The product of 2 decimals with like signs is positive. Unlike signs. The product of two decimal numbers with unlike signs is a negative. Example 4. Simplify. Negative 2 and 2200ths times negative 1 and 2300ths. Solution. Ignore the signs to do the multiplication on the left, then consider the signs in the final answer on the right. So on the left, we see as each factor has 2 digits to the right of the decimal point, there should be a total of 4 decimals to the right decimal point in the product. So if we treat the decimal numbers as whole numbers, we have 123 times 222. Multiplying these together, we get 16,206. Then we place a decimal point with 4 digits to the right. The like signs give us a positive result, so the product of negative 2 and 2200ths times negative 1 and 2300ths is 1 and 6,206 10,000ths. Example 5. Simplify. 5 and 6800ths times negative 12,000ths. Solution. Ignore the signs to do the multiplication on the left, then consider the signs in the final answer on the right. The first factor has 2 digits to the right of the decimal point, the second factor has 3. Therefore, there must be a total of 5 digits to the right of the decimal point in the product or answer. This necessitates prepending an extra 0 in front of our product. So, since 12 times 568 is only 6,816, we have to add another 0 to have 5 digits to the right of the decimal point. Then, since we're dealing with unlike signs, the product is going to be negative. 5 and 6800ths times a negative 12,000ths equals a negative decimal number result. Order of operations. The same rules guiding order of operations also apply to decimal numbers. Example 6. If a equals 3 and 1/10 and b equals negative 2 and 4/10, evaluate a squared minus 3 and 2/10 times b squared. Solution. Prepare the expression for substitution using parentheses. Substitute 3 and 1/10 for a and negative 2 and 4/10 for b and simplify. So we get 3 and 1/10 squared minus 3 and 2/10 times a negative 2 and 4/10 squared. We'll do exponents first. 3 and 1/10 squared is 9 and 6100ths. Negative 2 and 4/10 squared is 5 and 7600ths. Then we'll multiply. 3 and 2/10 times 5 and 7600ths is 18 and 432 thousandths. Then we'll subtract. 9 and 6100ths minus 18 and 432 thousandths gives us negative 8 and 822 thousandths. Powers of 10. Consider the powers of 10. Note that the answer for 10 to the 4th power is a 1 followed by 4 zeros. Do you see the pattern? In the expression 10 to the nth power, the exponent matches the number of zeros in the answer. Hence, 10 to the nth power will be a 1 followed by n zeros. Example 7. Simplify 10 to the 9th power. Solution. 10 to the 9th power should be a 1 followed by 9 zeros. That is, 10 to the 9th power equals 1 billion. Multiplying decimal numbers by powers of 10. Let's multiply the decimal number by 10 to the 3rd power, or equivalently by 1,000. Ignore the decimal point and multiply the numbers as whole numbers. The sum total of digits to the right of the decimal point in each factor is 6. Therefore, we place the decimal point in the product so that there are 6 digits to the right of the decimal point. However, the trailing zeros may be removed without changing the value of the product. That is, the decimal number times 1,000 is... Note that the decimal point in the product is 3 places further to the right than in the original factor. This observation leads to the following result. Multiplying a decimal number by a power of 10. Multiplying a decimal number by 10 to the nth power will move the decimal point in places to the right. Example 8. Simplify the decimal number times 10 to the 4th power. Solution. Multiplying by 10 to the 4th, or equivalently by 10,000, moves the decimal 4 places to the right. Thus, the decimal number multiplied by 10,000 gives us the new decimal number with the decimal point moved 4 places to the right. The circle. Let's begin with the definition. A circle is a collection of all points equidistant from a given point O called the center of the circle. The segment joining any point on the circle to the center of the circle is called the radius of the circle. In the figure above, the variable r represents the length of the radius of the circle. We need another term, the diameter of a circle. If 2 points on a circle are connected with the line segment, then that segment is called the chord of the circle. If the chord passes through the center of the circle, then the chord is called the diameter of the circle. In the figure above, the variable d represents the length of the diameter of the circle. Note that the diameter is twice the length of the radius. In symbols, the diameter equals 2r. The circumference of a circle. When we work with polygons, the perimeter of a polygon is found by summing the lengths of its edges. The circle uses a different name for its perimeter. The circumference of a circle. Length of a circle is called its circumference. We usually use the variable c to denote the circumference of a circle. That is, if one were to walk along the circle, the total distance traveled in one revolution is the circumference of the circle. The ancient mathematicians of Egypt and Greece noted a striking relation between the circumference of a circle and its diameter. They discovered that whenever you divide a circle's circumference by its diameter, you get a constant. That is, if you take a very large circle and divide its its circumference by its diameter, you get exactly the same number if you take a very small circle and divide its circumference by its diameter. This common constant was named pi. Relating the circumference and the diameter. Whenever a circle's circumference is divided by its diameter, the answer is the constant pi. That is, if c is the circumference of the circle and d is the circle's diameter, then c divided by d equals pi. In modern times, we usually multiply both sides of this equation by d to obtain the formula for the circumference of a circle. C equals pi d. Because the diameter of a circle is twice the length of its radius, we can substitute d equals 2r in the last equation to get an alternate form of the circumference of the equation. C equals pi times 2r equals 2 pi r. The number pi has a rich and storied history. Ancient geometers of Egypt, Babylonia, India, and Greece knew that pi was slightly larger than 3. The earliest known approximation date from around 1900 BC. They are 25 over 8, Babylonian, and 256 over 81, Egypt. The Indian text Shatapatha Brahmana gives pi as 339 divided by 108 approximately equals 3.139. Archimedes was the first to estimate pi rigorously, approximating the circumference of a circle with inscribed and circumscribed polygons. He was able to prove that pi is greater than 223 over 71 and less than 22 over 7. Taking the average of these values, he used pi approximately equals 3.1419. Modern mathematicians have proved that pi is an irrational number, an infinite decimal that never repeats any pattern. Mathematicians, with the help of computers, routinely produce approximations of pi with billions of digits after the decimal point. Digits of pi. Here is pi correct to the first 50 digits. The number of digits of pi used depends on the application. Working at very small scales, one might keep many digits of pi, but if you are building a circular garden fence in your backyard, then fewer digits of pi are needed. Example 9. Find the circumference of a circle given its radius is 12 feet. Solution. The circumference of the circle is given by the formula c equals pi d, or because d equals 2r, c equals 2 pi r. Substitute 12 for r. C equals 2 pi r equals 2 pi times 12 equals 24 pi. Therefore, the circumference of the circle is exactly c equals 24 pi feet. We can approximate the circumference by entering an approximate for pi. Let's use pi approximately equals 3.14. Note the symbol approximately is read approximately equal to. C equals 24 pi, approximately equals 24 times 3.14, approximately equals 75 and 3600 feet. It is important to understand that the solution C equals 24 pi feet is the exact circumference, while C approximately equals 75 and 3600 feet is only an approximation. The area of a circle. Here is a reasonable argument used to help develop a formula for the area of a circle. Start with a circle of radius r and divide it into 8 equal wedges as shown in the figure that follows. Rearrange the pieces as shown in the following figure. Note that the rearranged pieces almost form a rectangle with length approximately half the circumference of the circle pi r and width approximately r. The area would be approximately length times width, approximately pi r times r, approximately pi r squared. This approximation would be even better if we doubled the number of wedges of the circle. If we double the number of wedges again, the resulting figure would even more closely resemble a rectangle with length pi r and width r. This leads to the following conclusion. The area of a circle of radius r is given by the formula a equals pi r squared. Example 10. Find the area of a circle having a diameter of 12.5 meters. Use 3.14 for pi. Round the answer for the area to the nearest tenth of a square meter. Solution. The diameter is twice the radius. D equals 2r. Substitute 12.5 for d and solve for r. So r equals 12.5 divided by 2, which is 6.25. Hence, the radius is 6.25 meters. To find the area, use the formula a equals pi r squared, and substitute 3.14 for pi and 6.25 for r. So the area a equals 3.14 times 6.25 squared. First, simplify the exponent part. 6.25 squared is 39.0625. Then 3.14 times 39.0625 is 122.65625. Hence, the approximate area of the circle is a equals 122.65625 square meters. To round to the nearest tenth of a square meter, identify the rounding digit and the test digit. Because the test digit is greater than or equal to 5, add 1 to the rounding digit and truncate. Thus, correct to the nearest tenth of a square meter, the area of the circle is approximately 122 and 7/10 meters squared.